Now we have our final session for you, a special headliner taking us into this evening. It's considered to be one of 3 people most responsible for the advancement of deep learning from the 1990s and the year 2000s, with over 135,000 citations found by Google Scholar and HA index of 125. I'm really pleased to say joining us from Canada via Skype is Yoshua Bengio, the Professor of Computer Science and Operations Research at the University of Montreal. Yoshua is going to give us his thoughts on the challenges of deep learning towards AI. And then after Yoshua's presentation via Skype, we'll do a Q&A and also a special announcement. More on that to come, but I'm hoping with the power of technology. Yoshua, welcome.
Hey.
Good to see you. And I'm going to give you a very warm welcome from our crowd here in Amsterdam, and I'll let you take over.
All right, let's do screen sharing. Just a minute. So I'm going to tell you about what I perceive as some of the limitations of current research in AI and deep learning, especially as it pertains to understanding and in particular understanding language. So you see my slides all right?
Can you?
Okay. So, you know, the main advances that have happened in the last few years in AI are mostly in the area of perception. So computers have made huge strides there. Of course, this is changing vehicles. This is
brave enough to do the. I thought it was just nice to hear.
This is also some progress in the ability of computers to manipulate language. For example, here to translate an image into a sentence and to play games. As you know, the champion in the game of Go has been beaten by a computer using deep learning. Also, the way that we even think about these deep nets has changed from pattern recognition devices to systems that can actually be creative. So what you're seeing here are images of people that have been invented by the machine. These are not real people. They were not, taken from some database. They were synthesized by these generative adversarial networks that we initiated in 2014. And you see the progression over years as the quality of these generated images has been improving. Another really important improvement that has happened in the last few years is due to the use of attention mechanisms, which are inspired by human cognition, of course. And in our work on machine translation, we found that a particular form of attention mechanism, which we call content-based soft attention, made it possible to get much, much better results. So what happens is that as the system is producing the next word in the translated sentence, it's using its attention mechanism to focus on one or a few words in the source sentence. And this ability to focus on just a few elements has been found to be useful in many areas, and transforming deep learning from, just processing vectors to processing any kind of data structure. The progress on machine translation has been pretty incredible. What you see on the bottom is the quality of human evaluations, starting from the traditional n-grams that were there, the standard before 2016, to when Google installed this in the Google Translate, approaching substantially the level of human quality translation. Now, all this is really great, and we are amazed at the progress that has happened, but we have to keep our heads cool, because in spite of all this, we're still very far from human-level AI. And this is best seen when you look at the kinds of mistakes that these systems make. So, for example, what I'm showing here are well-known so-called adversarial examples, where you tweak a little bit the image on the left to produce the image on the right. And instead of saying that this is the image of a dog, the system would say it's an image of an ostrich, but it's been tweaked to produce that answer. There are other settings that have been studied showing that the systems we're currently training, although they seem to be doing a good job on the data that we're training on, are not really capturing the sort of high-level abstractions that humans rely on. For example, if you ask them to classify these sentences in order to decide what they refers to, like in the women stopped taking pills because they were pregnant, is they women or pills? If you change pregnant to carcinogenic, the answer changes. And humans are very good at answering these kinds of questions, but current machine learning systems are barely better than chance. One thing that clearly is lacking in current AI is intuitive psychology and intuitive physics. The kinds of things that we don't really need to explain with language, but that babies and young children learn by themselves by observing the world and interacting with it. And you don't need to teach them these things. They just learn these things by themselves. And these are things that we know, but we don't have conscious access to, so we can't talk about it, we can't explain it to computers, we can't program them to do these things. So when asking what is missing from current AI, and in particular, trying to understand what would be needed for a machine to actually understand a question or understand a document, the central question I want to focus in on is what kind of knowledge is needed for this to happen? And then how is the computer going to acquire that knowledge? Now, a lot of current natural language processing in machine learning is based on training on tons and tons of data of mostly of text corpora, right? So large quantities of texts, sometimes much more than a human could read in their whole lifetime. And yet they're still not understanding things nearly as well as we do. So to maybe get a glimpse of what is going on, I propose the following thought experiment. Imagine you're approaching another planet and you're going to be observing the aliens on that planet and trying to figure out their language by looking at the bits of information that they're exchanging with each other, so their language. Now, this is actually what we do when we train a neural net to model texts. We're trying to figure out the meaning of the text by modeling the distribution of sequences of words. Now, on that planet, however, things are a bit different from Earth. Their communication channel is noisy. Their communication channel is not noisy, whereas our communication channel is noisy. And so like on Earth, on this planet, the bandwidth is expensive, so you want to minimize the number of bits that you're sending back and forth. And so the right way to do this is to compress the messages as much as possible. However, we know that if you can compress a text, for example, or any kind of information as much as possible, what you get is a sequence of bits that look like noise. They're independent. There's no information that you can recover by just looking at those bits of information that are the result of compression. So that's a problem, because even though on Earth we have noise in our communication channel, which is speech, and so there will be some redundancy in the words that we exchange, and so maybe there is some information there about meaning, it's very likely that we're missing some information about meaning just by observing lots and lots of texts. So how do we manage to train a system to understand that alien language? Well, what we could do is, instead of just watching the signals that they exchange to communicate, we try to observe their behavior. So we try to figure out what their intentions are. And look at the context of the messages that they're exchanging. So now we have a bit more work to do. In addition to modeling the texts, we have to model the behavior of these aliens. We have to model their world. We have to understand the causal structure of their environment and of their intentions. This is a lot more work, but unfortunately, I think that's the only way we're going to build machines that understand these aliens. And similarly, I think we have to do this sort of grounded language learning in order to have machines which understand human languages. So that means we need to spend a lot more effort on building machine learning systems that can understand their environment, which can understand how the world works, and then associate the language, the sentences and so on, with the context to which it refers, to basically associate for example, the objects in images with the names of these objects in a sentence, but of course much more than only the names, but also more complicated constructions and things that are happening in the world around us. So this is connected to an issue in machine learning. If you look at the progress we've made with deep learning, it corresponds mostly to this type of cognition called System 1, which is the things you can do very quickly, like in half a second. That's mostly heuristic, unconscious, so you don't have access to why you're doing it and how you're doing it in detail, and not linguistic. So like how I recognize an object in front of me isn't something I can break down into pieces that I can then explain to a computer. But deep learning does these things very well. However, there's another kind of cognitive processing called System 2, which corresponds more to what classical symbolic AI was trying to do. And that's the kind of thing that takes us more time, that's usually sequential. For example, if I ask you to add two large numbers, it's conscious, it's logical, it's linguistic, we can talk about it. Algorithms are like this, like it's a recipe we can describe and we can reason about. So we are not doing as well right now in machine learning on System 2 types of tasks. But as far as language is concerned, of course, this is very important. So I think it's going to be really necessary in the future to combine research on both systems. Now, as far as the part about building systems that understand our environment, there's really a lot of excitement in recent years in reinforcement learning and other agent learning methods, which for now is being tested and evaluated on virtual worlds, virtual environments like video games or these 3D worlds that people have built. And the idea is that we're not really trying to build a full understanding of the whole world, but to design learning algorithms that can explore the environment, try things, and learn from those experiments. And we can test these algorithms on these simpler worlds, and we can have a fast research cycle. And then as we get better at it, we can test these algorithms with more complex environments and eventually try this on real world environments like robots. So I think what is going on right now with the kinds of mistakes that I showed you earlier that deep learning is doing is that the current models cheat by looking at clues and some sort of regularities like the backgrounds and the texture, but they don't work so well in examples that look very different from the training data, whereas humans are very good at that. For example, you can project yourself, if you read a science fiction novel, so you can project yourself if you were on the moon, and you can imagine what would be the consequences of being there, because you understand the causal mechanisms that govern physics, say, of being in the moon. And so this is something that machine learning is starting to study, how to capture causality, but we're really not good at yet. And I think it's going to be really important to predict the future far from the type of data that the machines have seen. So in my group, we have started a project which I call the Baby AI Game Project, which is one of these virtual environment benchmark where we're trying to test different reinforcement learning and agent learning and imitation learning, unsupervised learning methods, where the agent is trying to understand its environment, but it's also able to interact with the human. And the human is a player whose role is to help the baby learner to figure out its environment using natural language. So we've created an environment where the baby has to execute some missions, things like go to the red ball, open the door on your left, put a ball next to a purple door after you put the blue box next to a gray box, and pick up the purple box. Whew. Well, even these very simple environments and simple missions are currently out of reach of the current machine learning. So I think that there's much that can be achieved by testing our methods on these simple grid worlds and eventually 3D environments before we actually try them on much more complex, rich environments of the real world. So to conclude, I've tried to make a list of some of the research directions which I think are going to be necessary to make substantial progress towards human-level understanding. So of course, we're going to need a lot more computing power because the models we're building are going to be big in proportion to how much knowledge needs to be compiled into them. And right now, we're only training models that capture very small aspects of our reality. Also, in order for these agents to be able to discover how the environment works, a lot of that is going to be unsupervised. They're going to be exploring their environment and discovering underlying causal factors and causal mechanisms. So we need progress on both of these aspects of machine learning. Regarding language, we can't have these systems learn language in a way that's abstracted away from what language refers to. And that's why we need more research on grounded language learning. These agents need to be like little scientists or children who are trying to understand their environment by testing ideas and hypotheses so as to quickly figure out how things work and discovering the relevant high-level concepts. We also need to bring together the sort of classical AI or goals of system 2 cognition with the kinds of deep learning representations that correspond to system 1 cognition that we have achieved in recent years. So that's it. Thank you very much.
Oh, there we go.
Let me switch.
Yoshua, thank you very much indeed. I think the technology will mean that if you unfreeze from your presentation, we get to see you. Yes, wonderful. If it's okay with you, we've got a few minutes to open up questions to the floor, if that's okay. So if I can invite you to raise your hands if you'd like to ask Yoshua a question, please do. Again, we've got our roving microphones here. Gentlemen, just here at the front. And anybody else, raise your hands, and I'll keep an eye on where the hands are.
Thank you very much for the talk. Basically, to be honest, you're the reason that I buy the ticket to the conference. But it's a
He's
pity
the reason you bought a ticket?
Well, yes.
Amazing. A big fan.
But it's a pity that you cannot be here. But
Sorry.
My question would be, for the reinforcement learning that we train our model on, would you have tips on how do we design the representation of those virtual environments for our model?
You mean how we design the environments?
Yeah, how we design the environment.
Absolutely, yeah. So that's a very good question. I think the important ingredients are compositionality. So the environment needs to have many different factors and mechanisms in it that can be combined in many ways to present a real challenge to the learning procedures. Otherwise, what happens in a lot of reinforcement learning experiments that seem to work quite well is that the agent just sort of learned by heart some solutions, like playing a particular game, and they find a trajectory that solves the game. But there's not much generalization. So we have to be really careful in setting up environments where the only way that the learner can really learn is by being able to figure out the actual underlying mechanism to really understand. So they have to be tested in a way that's very different from their training data. And so you need some sort of compositional structure in the way that the environment is defined. Like, for example, I showed this environment